In this presentation, we will discuss shear stresses and shear strains. Let us recall what we discussed previously. We took a body which was subjected to set of loading. The body was supported at different locations. We said that in order to find out internal stresses, we can cut the body at a particular location. After that, we can omit part of the body and consider the effect of omitted part onto the remaining part of the body. So we are trying to work out now stresses at a particular surface of interest. Please note, once we cut a body, we get a surface and all the forces or stresses are appearing on the surface. If we average out all the stresses or forces on the surface, we can have resultants of three forces which are aiming in three different directions of the Cartesian coordinate system. And in addition to that, we would have some moments in all the three directions. These moments can be further decomposed into couples. So to cut long story short, we end up with a cube which has got six faces, and every face is made up of three different type of stresses. One of the stress is axial and the other two are shear. The axial stress is directed outwardly from the surface. However, the shear stresses are lying within the surface. It is customary to define shear stress in terms of two subscripts. The first subscript is the outward drawn normal of the surface we are interested in. And the second one is the force direction which is causing the particular stress. So, for example, tau yx means that the surface of interest is the one having outward drawn normal in the y direction, and the stress is generated by the force whose direction is in the x axis. Similarly, tau yz will mean that the surface of interest is having outward drawn normal in the y direction and the force causing tau yz is in the direction of z axis. Tau yz and tau yx, these are average of all the forces which are acting on our surface of interest. So the stress component that acts in plane of the section area is the shear stress. In order to show that this stress can develop within a body, we take this body which is supported by two other bodies. We apply the force F onto this body. This force F has a tendency to punch through, or in other words, at these two areas, we can have shear stresses getting developed. If this force is extensively high, then the capacity of this body at these 2 points, at A and C, we can have a shear failure where this lozenge will shear through the remaining body and we will get something like this. So now this cube or lozenge is shown separately over here. We have this force getting divided into two shear forces. Please remember that these shear forces are the result of infinite number of small shear forces within the area. So this shear force is the resultant of all the shear forces. Please note that in the case of axial stresses, we could have either the extension or stretch of a member or squish of a member. But in the case of shear, we can have a portion of a body which has slided against the remaining part of the body. The average shear stress distribution over the sectioned area that develop this shear force is defined as tau average is equal to V by A. Once again, Please note that the force F is divided between these two sections. So V would be F by 2. So for a particular cross section, we would have F by 2 force applied. And area is the area of this cross section. The loading case, which we have discussed over here, is a perfect example of a simple or a direct shear, since shear is caused by the direct action of applied force F. The shear of this type occurs in many simple connections such as pins, welding materials, bolts, etc. Now let's discuss the shear stress equilibrium. So we have got again the same body and we pick out this cube from this body. We assume that the face of our interest, or that face which has been cut, is made up of infinite cubes like this one. So we will consider this cube without considering the axial stresses. Every cube within the surface of interest should be in equilibrium. So if we say that summation of all the forces about y must be equal to 0, so that would mean that tau zy times the area of this space, which is delta y into delta x, minus tau zy into area of this face, which is delta x times delta y. These two will cancel out and we will get these two forces equal. In a similar way, if we take summation of moment about x-axis is equal to 0, so the couple caused by these two shear stresses will be counteracted by these two shear stresses. Please note that couple is normally by forces, not shear stresses. So these shear stresses have to be converted into forces and then multiplied by the lever arm. So the shear stress tau zy times delta x delta y gives the force, and that has to be multiplied by the lever arm delta z. Similarly, the yz, which is this one, multiplied by delta x delta z into delta y must be equal to 0. These both cancel out, and in the end we get tau zy, tau dash zy, tau yz, tau dash yz all equal to tau. So we can say that all the four shear stresses must have equal magnitude and be directed either toward or away from each other at opposite edges of the element as shown in this volume element. This is sometimes called as the complementary property of shear. An element in this case is subjected to pure shear. Now, in order to make the shear stress concept more clear, let's consider a simple example. We are asked to determine the average shear stress in a 20 millimeter diameter pin at A and 30 millimeter diameter of pin at B. This member is supported at A and B. At B, we have got a cable which is attached to point C. 30 kilonewton load is applied at 2 meter from the left support. Now, as we can see, this member can have three reactions. One is FB, another one AY and AX. We can take summation of moments and summation of forces in order to determine these reactions. If we take summation of moment about A equal to 0, we would have the sign of FB contributing to the moment. So FB into 4 by 5 times the lever arm 6 minus 30 into 2 will give us FB is equal to 12.5 kilonewton. Similarly, once FB is found, AX can be worked out by using summation of all the forces about X must be equal to 0. So AX will come out to be 7.5 kilonewton. And we can determine AY by taking moment about point B or taking summation of Fy equal to 0. AY comes out to be 20 kilonewton. Now please note, in order to find out the force at A, we have to take resultant of AY and AX. So FA is equal to AX square plus AY square, which has been worked out as 7.5 and 20. So the resultant comes out to be 21.4 kilonewton. Now AX look like this one. So we have got two brackets which are connected by a pin. The member force is 21.36 kilonewton, which is applied in this direction, in the axial direction, as we have seen over here. The resultant force is 21.4 kilonewton. This resultant force will be divided between two cross sections over here because we have got two areas taking the shear, as we can see from this arrangement over here. So the member is pinned into these two brackets, and if this if AX or if FA is applied in this direction, we have two areas of this bolt resisting the force FA. That's why the FA has to be divided by 2 in order to work out the shear at one cross section. So FA is divided by 2, we get 10.68. VB, on the other hand, is having this type of arrangement. So we have the web of this beam which is pinned to a cable. We have only one cross section this time taking the shear. So 12.5 kilonewton load will be taken by one cross section, which is as shown. PB is 12.5 kilonewton. After that, we can find out the area of cross section of pin at A and area of cross section of pin at B. So at A, it's a 20 millimeter pin, and at B, it's a 30 millimeter. Pi d square by 4 will give us the area. So we take this force and divide that by area and get 34 megapascal at A and 17.7 megapascal at B. There is another example where we have a wooden bracket which is pulled by 6 kilonewton. This wooden bracket is housed inside another bracket. So since this bracket is being pulled, the point of contact at the top and bottom will resist this pull out. So 6 kilonewton will be halved by top and bottom contact points. In order to find out the shear plane at AA and BB, we will have to get the area of cross section at AA and area of cross section at BB. After that, we will multiply that by, after that, for AA, we will divide the 3 kilonewton by the area of cross section at AA, and for BB again 3 kilonewton by the area of cross section at BB. At AA, the length is 0.1 meter and the thickness is 0.15 meter. So 3000 divided by 0.1 times 0.15, which is the area, will give us the stress over here. And similarly, we can find out the stress at BB. Now, let us discuss shear strains. So as we have discussed that at a surface of interest, we can't only have axial stresses, we can have shear stresses. So correspondingly, we will have shear strain. The shear strain does not cause a line segment to elongate or contract, but they cause the line segment to change its direction. If we select two line segments A, B, and C on the body, which is supported, so before applying load, we have A, B, C, two line segments. After applying load, the angle between AB and AC changes. The change in angle is referred to as shear strain. Please note, this configuration is before application of the load and this one is after application of the load. So if these two sides AB and AC are the sides of a rectangle, after deformation they become side of a parallelogram as shown over here. For a shear deformation, it is important that both the sides move. So we write gamma is equal to pi by 2 minus theta. In other words, gamma is equal to the angle A plus B. If we assume that initially AB and AC are orthogonal to each other, then if theta is bigger than pi by 2, after deformation, our gamma is positive. If theta is less than pi by 2, Our gamma would be negative if theta is bigger than pi by 2. Thus, summing up our argument, in a volume element, we can have normal strains which are in the normal direction to the surfaces, and we can have shear strains which involve the change of the angles of the surfaces. So the normal strain within the x direction will cause 1 plus strain x times delta x length after the deformation, 1 plus strain y delta y. Thus, if we consider a volume element, we can have altogether normal strains and shear strains. The normal strain will try to change the volume of the element. If this element is having initial sides of delta x, delta y, delta z, the final length of the side delta x after deformation is 1 plus strain x delta x. This is actually delta x plus the change in length delta x times strain x. So this is the final length of delta x. Similarly, the final length of delta y and delta z are as shown over here. All these three strains are normal strain which produce change in the volume of the element. The change in shear strain, on the other hand, is equal to pi by 2 minus gamma xy, pi by 2 minus gamma yz, and pi by 2 minus gamma xz. The shear strain produces change in the shape of the element. Let us solve one problem to discuss this further. So we have got a plate shown and that is fixed along AB and held in the horizontal guide at its top and bottom, AD and BC. So it can't move anywhere on these three sides. If the right side, CD, is moved by 2 millimeter, so there is a horizontal displacement of 2 millimeter, determine the average normal strain along the diagonal AC and the shear strain at E relative to x and y axis. So in order to find out the normal strain along the diagonal AC, we take the original length AC and the final length A dash C dash, or AC dash, because A stay at the same position, C dash moves, so we can call it AC dash. AC is using Pythagoras theorem, so we have 0.15 square plus 0.15 square under root. AC dash, on the other hand, is equal to 0.15 in the y direction and 0.76 in the x direction. AC dash, on the other hand, is 0.15 in the y direction and 0.152 in the x direction. So BC dash is 76 plus 76, which is 0.152 whole square, and everything under the square root. So strain along AC is change in length by original length, which is the final displacement 0.213 minus 0.212, which is this one, divided by 0.21213. So we get 0.00669 millimeter per millimeter. In order to find out the shear strain, we can take this angle. So tangent theta by 2 is equal to 75 by 7. So in order to find out shear strain, we can simply take tangent theta by 2 is equal to 76 by 75, which is shown over here. Now we can take inverse of this and then multiply 2 with this one in order to get theta equal to 90.76 degree. This can be converted into radian by multiplying pi by 180. After this, we can find out our gamma xy, which is pi by 2 minus theta, which is 1.58. This comes out to be minus 0.0132. We discussed previously that if theta is greater than pi by 2, then gamma is negative. And it does make sense that theta will increase if we stretch this body. That's why we get gamma negative. That's all for shear stress and shear strain. Thank you.